Hello and welcome to lesson 15 of this Introduction to Probability of Wolfram. The topic for this lesson is the multinomial distribution. Let's begin. The binomial distribution is at the center of discrete distributions so far. But if you remember lesson 2, the word binomial refers to the fact every trial has two outcomes. Naturally, you can extend these trials to more outcomes, and this leads to the multinomial distribution, the probability of I successes out of n trials with m possible outcomes. As you can see here, the PDF is simply an extension of the binomial distribution. In this lesson, you'll see how to compute multinomial expectation, probability, estimation, and simulations. This is the first multivariate distribution of the course, so let's think about it for a second. Multivariate means the distribution does not give a value but a list of values, which is usually visualized as each probability being a point in a given number of dimensions. For example, a single baseball match may have a quantity of home runs, of hits, and of strikeouts, making each match a three-dimensional point, and so a three-dimensional distribution. The binomial distribution is restrictive because it's limited to two outcomes. But naturally, choosing in more than two categories results in a multinomial coefficient. Then, for a given category, the probability of getting it I times is the probability of selecting that category power I. If you repeat this for all categories, then you obtain the PDF. You can plot the multinomial distribution using the built-in discrete plot 3D and the multinomial distribution function. Notice that this not only resembles a binomial in 3D, but this is a binomial in 3D. Think about it. The multinomial for two variables only chooses two groups, which is the equivalent of the binomial implicitly. What does a mean look like in a multivariate context? Well, if you have a list of variables, you also have a list of means. The mean of the multinomial, like the binomial, is the expected success of n trials, with this time the probability k of the kth variable. So you have the binomial mean with each variable. It's the same concept for the variance, as you can see here. The multinomial is frequently used when the events are discrete in a discrete sample space. Each probability p is known and constant, and there are multiple classes. Indeed, for any trial, there needs to be more than two possible outcomes. In terms of datasets, this distribution is frequently considered for ordinal or discrete datasets over multiple attributes. Okay, enough theory. Let's apply. Imagine there's 10 red balls, 13 blue balls, and 20 green balls in a bag, and you take 3 balls at random. What's the probability of getting 3 green balls? Take the probability of taking 3 green balls, considering your 3 variables are multinomially distributed for a sample of 3 with the corresponding probabilities. Okay, let's take another example. Imagine a residential area where there are 73%, 20%, and 7% of family homes, apartment buildings, and commerce buildings, respectively. If 5 fires are reported in different houses, what's the probability of at least one fire happening in each building type? Take the probability of having at least one of each type, considering your 3 variables are multinomially distributed over the sample 5 for a corresponding 0.73, 0.20, and 0.07 proportions, and you get around 18%. For expectation, let's roll some dice. What would be the expected sum of 2 dice? Consider that each face of the die is a possible outcome with a value, and the values go from 1 to 6. and each variable is a part of the multinomial distribution where all the faces have a probability of 1 over 6. And you get 7. What about blackjack, a game where you draw cards from a standard deck to reach a total value of 21? And we'll assume the ace, the jack, the queen, and the king are all worth 10. Assume you take 3 cards randomly. Then what's the expected value? Take the expectation of each card from 2 to 10, considering each card has a probability of 1 over 13, besides the last card of value 10, which will actually give a probability of 5 over 13 to account for the card 10, jack, the queen, the king, and the ace. And you get the answer. Many lotteries nowadays give multiple prizes. Let's say you buy 10 lottery tickets for $5 each for a chance to win at most one of many prizes: $10 million, a house of $300,000, a car worth $50,000, or a coffee coupon worth $3. For each, there's 1, 10, 20, and 200,000 winning tickets respectively. 10 million tickets were sold. Then what's your expected return on investment? Take the expectation of the sum of the value of each prize minus the cost, considering the probability of each prize and the probability of a losing ticket, and you have, on average, a loss of $35.40. How can you simulate a multinomial distribution? Just use random variate on your distribution. Okay, but now how do you visualize it? Depending on the dimensionality of your distribution, you might not be able to visualize the distribution. So to visualize it here, using a histogram, we just plot the two first variables, and so you get a partial understanding. To estimate the multinomial distribution, load the data and estimate it using the estimated distribution. Notice for multivariate distributions, you can't use the find distribution function, as this only applies to univariate distributions. So you're forced into using estimated distribution in this case. As always, you can verify those results by plotting the data against the estimation. So in summary, a multinomial distribution describes a probability of I successes out of n trials with n possible outcomes. To solve discrete distributions with more than a binary choice, use the multinomial distribution function. But so far, all named distributions were discrete. What about continuous distributions? You'll start the next section with the simplest continuous assumption: uniformity.